Welcome guys to this new video. So now I have gathered the mechanics questions from topics A, 1, 2, and 3 from the May 25 exam session. So the time zone 1, time zone 2, time zone 3 papers. These three questions appear in both the SL and the HL paper. So let's work through these questions. So in question 1, we have this graph. We are told we have a car of mass 1600 kilograms and it's accelerating from rest. It is important, and we have the resultant force acting in the direction of the motion of the car, and it's plotted against the distance traveled by the car. In part 1, we are asked what is represented by the area under the graph. So what's very important is that this is the resultant force and it's in the direction of motion of the car. So what we know is that the work done by a force is the force multiplied by the displacement in the direction of the in the direction of the force that we have. So basically we have the car over here, and then the displacement is obviously going to be this way, and the force is acting in the exact same direction as our displacement, so we don't need any angle here or anything. We always just need to look at the component of the force that is parallel with our displacement, and here they are originally parallel already. So the area under the graph simply represents the work done on the car. The work done on the car, and well, it's the area because again we have force on the y-axis and we have distance on the x-axis. So whenever we find an area, we always multiply the two axes in terms of units. And like if you imagine finding the, for example, the area of this rectangle over here, we also multiply the two sides. And the same for the triangle, but there we also add a 1/2. So even unit-wise, we will get Newton meters, which is joules. So that corresponds correctly. And then we have to calculate the final speed of the car. So what we know is that the car has started from rest, which means that all the work that this resultant force is doing on the car is increasing the kinetic energy of the car. So at the start we have zero kinetic energy, so all of the work that is done by the force is being converted into kinetic energy of the car. So from that we can determine the speed of the car. So let's find the work done by the force. So for that we need to find the area. So for the area, what we will do is split it up into two shapes, this rectangle and this triangle. Although we could see that this is a pretty regular polygon, there's a way to calculate its area easily, but I'm just going to split it up like this. So I see that I have a rectangle here. It's very important to notice the units on the axis. So this whole thing is actually times 1,000. So for the rectangle, the base is 60 meters, and the height is 3, and then here it's important, it's 3 times 10 to the 3 newtons. And then the triangle, well, the height of it is the same. And I can see that the base of it is from 60 to 100, so 40. And well, since it's a triangle, I will multiply it with 1/2. So if we plug this in, then we will get 2.4 times 10 to the 5 joules. And so this is the work done by the car, and this will be equal to the kinetic energy gain of the car. So this will be equal to 1/2 mv squared. And again, we are given the mass of the car to be 1600 kilograms. So we can simply calculate the speed. It's just going to be the square root of 2 times 2.4 times 10 to the 5 divided by the mass of 1600. So if we rearrange that, we get this. And if we plug this in, then we will get that this is 17 meters per second. So that's how we can determine the final speed of the car. And then this is continued here. So we are told that a different car travels on a horizontal road with a constant speed. And the engine develops 140 kilowatts. There's a resistive force acting on it, which is some constant times the speed of the car squared. And we need to determine this this constant, this coefficient of drag pretty much, and state its fundamental SI unit. So what we need to notice here is that since we're traveling at constant speed, it means that there is no net force, which means that the power developed by the car is completely opposed by the resistive force Fd. So they're the same in magnitude. So what we can say here is that if we multiply this resistive force by our, so this resistive force is basically equal to the power developed by the car. And so if we know this force and if we would multiply this with a v, so we know that power is just force times velocity. So if I multiply this force by velocity, then I get the power that I developed, which I know is 140 kilowatts. So I'll just use 140 and then I'll convert to SI units, as we want C in SI units. So this is the power developed, and this is equal to our constant times our velocity squared times velocity, so velocity cubed. So from this I get that C is 140 times 10 to the 3 divided by my velocity squared, so velocity cubed. This will give me 1.5. Now just the question is, what is my unit? So what I would probably do here is say that C is like a force divided by velocity squared. So let's think about the SI units here. So force is mass times acceleration. Mass is kilograms. Acceleration is meters per second squared. Velocity is meters per second, and we square that, so that will be meters squared per second squared. So this will be the units, and we can see that the seconds cancel, and one of these meters will also cancel. This will cancel with this squared, so this will just be kilogram per meter. So kilogram per meter. So that's how we can solve that question. All right, so this was from the time zone 1 paper, and well, this is the mechanics question from the time zone 2 paper 2. So let's see what we can do over here. So here we have a card X with a mass of 3 kilograms. So this is 3 kilograms and it's moving at speed 6 meters per second, and this is 6 kilograms. Now we have a spring attached to X. And we are given a graph showing the velocities of X and Y before, during, and after the collision. So it's just basically a velocity time graph over here for the cars. Told the collision lasted 40 milliseconds. We need to show that the collision was elastic. So for this, we need to know what an elastic collision is. So it's good to remember, elastic collision is just where the kinetic energy of the system is conserved. System is conserved. The opposite of this is a inelastic collision where the kinetic energy of the system is not conserved. So this is what we need to check. So we can see that at the start we only had kinetic energy from this X car. It only has a speed of 6 meters per second. So the kinetic energy at the start, I'll just label this as a position 1. So the kinetic energy here is just 1/2 times the mass of car X times the velocity of car X squared, and this will be 54 joules. And then part 2, where after the collision we need to see what kinetic energy we have, and ideally these will be the same. So we see car X with a speed of 2 meters per second and car Y with a speed of 4 meters per second. So the total kinetic energy will just be 1/2 times 3 times 2 squared for car X plus 1/2 times 6 times 4 squared for car Y, and this will be 54 joules. And well, we see that these are indeed the same, so there was no kinetic energy lost in this collision. Okay, in part B, we need to determine the magnitude of the average force exerted on Y. So what I always say is that if we have some force and time, if we have time and force related, then usually we need to grab onto Newton's second law, which stated that the net force is equal to the rate of change of momentum of an object. And we know momentum is simply mass times velocity. So in this case, the mass of car Y is obviously constant. It's the velocity that is changing, and we know that the collision lasted 40 milliseconds. So we just have to see that in this 40 milliseconds, how much did the did the speed of car Y change? And well, we see that at the start it was 0 meters per second, and it went all the way up to 4 meters per second. So the change in velocity was 4 meters per second. So the force is just going to be delta P over delta T, which is mass times delta V divided by delta T. Our mass was 6 kilograms, our change in speed was 4 meters per second, and the time of the collision was, the time at which the force acted for was 40 milliseconds, so 40 times 10 to the minus 3 seconds, and this will give me 600 newtons. Then in part 2, we need to calculate the average power delivered to Y. So average power is just we can calculate that either by seeing how much kinetic energy was transferred to the car and seeing how much time that took, as power is energy over time. So if we see how much kinetic energy the car gained, we just assume that it gained that amount of kinetic energy like linearly with time, so we just divide by 40 milliseconds and we get the average power. Or we can consider that well, the change in velocity, as we said, was 4 meters per second, and so the average speed is 2 meters per second. So what I can say is that the average power is just going to be the average force, which, oops, not in this question, part 2 only for now. So we have calculated the average force. The power will just be the average force times the average velocity. So the average force was 600 newtons, and the average velocity was, well, 0 plus 4 over 2. So just, times 2. So this will be 1,200 watts. If you're curious, then what you can also do is calculate the gain in kinetic energy of the car and divide that by the time. That should give you the same solution. So just calculate with the 4 meters per second squared over 4 meters per second over here and see that it gained that kinetic energy in this 40 milliseconds. Okay, and then we need to find the elastic energy stored in the spring. It is equal to 30 milliseconds. So here, what we need to really remember is energy conservation. So the energy during this entire collision is energy is conserved. So we saw that before and after the collision, we only have kinetic energy, but during the collision, we can also have elastic potential energy. So we need to see how much kinetic energy is in the system, as the rest of the energy will be the elastic energy. So the E total is at 30 milliseconds is the kinetic energy of car 1 plus the kinetic energy of car 2 plus the potential energy stored in our spring. And we know that the total energy is 54 joules. As for example, in part A, we have calculated at the start all the kinetic energy, all the energy we have is inside the kinetic energy of car X. Okay, so let's see what their speeds are. So we see that both cars have a speed of 2 meters per second at 30 milliseconds. So the kinetic energy of the two cars is just going to be 1/2 times 3 plus 6. So I have just factored out the 1/2 and the mass of the two cars because their speed is the same. So I can just write it like this. And this will be, we have to add potential energy, and this will be 54 joules. So if we calculate this, this will be 18 joules. So I just subtract this from 54, and then we get that the potential energy is 36 joules. So again, energy conservation is what we really have to remember over here. Okay, and then the time zone 3 mechanics question we have a box of 1.2 kilograms lying at rest on the surface. We're told the coefficient of static friction and the coefficient of dynamic friction. And in part A, we need to outline why the coefficient of friction has no units. So we need to remember that coefficient of friction is basically just the ratio of the frictional force and the normal force, like this. And well, since it's a ratio of two forces, the units of the forces will cancel out, so it's basically unitless. So it's just a ratio. So it's a ratio of two forces, and therefore the units cancel. So we simply have newtons over newtons. So that has just a unit of 1. So if I actually want to be really precise, coefficient of friction does have a unit. It has a unit of 1. Because we can multiply coefficient of friction with other quantities. And for example, if I multiply the coefficient of friction with a force, then I cannot say that I'm multiplying no unit with newtons. That doesn't really make sense algebraically. So that's why we say it would have a unit of 1, because 1 times newton is simply newtons. So we have to be very precise. We should say it has units of 1. But okay. In part B, we need to show that the minimum force needed to accelerate the box is about 4 newtons. So the minimum force, we have to determine what frictional force we need to overcome so that the block starts moving. And well, that's the coefficient of static friction. So the force we need is simply the FF max. And again, this comes from the static friction, as this is the frictional force that is acting before the block starts moving. So the frictional force is just this coefficient times the normal force. And well, since we have a block that is at rest on the surface, the block is not moving vertically, and therefore the sum of the vertical forces has to be 0, and therefore the normal force in this case is equal to the gravitational force mg. There's no net force in the y direction, so they have to be the same. If you haven't seen an example like this, the normal force is not equal to the gravitational force. For example, if we have an incline and we have a block on it. So if you see an example like that, then there's a different way of determining the magnitude of the normal force is not equal to the gravitational force. And that's just why I'm saying that here, this is why Fn equals mg, because vertically there's no force. So this mu times mg, so 0.36 times our mass of 1.2 times 9.81 will give us a force of 4.2 newtons, which is approximately indeed 4 newtons as the question wants. Okay, here we have a force of 14 newtons acting on the box for 0.35 meters. And then the force is removed and the box comes to rest after displacement d. We need to determine this distance. So as usual, there's two approaches here. There's an energy approach and there is a Suvat approach. What I'll do here is show the energy approach and briefly explain how the Suvat approach would work. So what we know is that, again, energy is conserved. So once the force has pushed the block this distance, it will have done some work. And what we need to remember here is that there's constantly a frictional force acting on the block, right? That is why the block will eventually slow down, because the frictional force will kind of eat away from our kinetic energy that we have gained. So the frictional force, firstly, is not the same as the previous question, because now we are moving, so we need the dynamic friction. So there's a smaller frictional force once we start moving. So dynamic friction times mg. That will give us 3.29 newtons. And well, the question is, how much net work do we supply to the box during the 0.35 meters? So the work done on the box, well, this force does positive work because it's pushing the block, whereas the frictional force is kind of opposing it. So the net force that is acting on the block is 14 minus 3.29. And this is multiplied with the distance that we have traveled. As again, work is force times distance, just like I explained in the first question from the time zone 1 paper. So this is times 0.35. This will give us 3.75 joules. And now we have removed this force. So this frictional force alone will now take away all of this energy that we have gained. So the distance, so we could say that the work done by the frictional force in the second section is the frictional force times D. So D is just our energy, 3.75, divided by our frictional force, and this will give us 1.14 meters. So pretty much during this section we have gained some kinetic energy, and all of that kinetic energy is taken away by the frictional force in this distance. Okay, so now this is just a HL section. Now this is to do with rigid body mechanics. That's 2 short questions, so the SL students don't have to solve this anymore. So now we have a box that is standing up. We're told the height and the width of the box, and we have a person pushing the box with a force of F until the box slips without sliding. I mean, the box tips without sliding. We need to determine this force. So we need to consider the moments in this, or the torques in this moment, in this section. So we need there to be a net torque acting on the block that will make this rotate. So let's consider what forces we have acting on the block. We have the gravitational force, mg, and of course we have our pushing force. And what we will do here is that in the moment that it's about to tip, we will see what this force has to be. So I will write the sum of the torques around this point V, because again we're assuming that it's going to turn around. This will be the pivot of our motion, and we want to find the force where it's just about to tip. So we're kind of looking at this case where it's not really on the ground, but it's also not really tipped already. It's kind of in between, and that's why we don't need to consider the normal force over here, because the moment that it tips, there will be no normal force anymore in the middle of the block over here, so that will not have a torque. So let's consider, we know torque is just force times the distance, where these two are perpendicular. So the distance is always the shortest distance between the line of action of the force and the axis of rotation. So what I like to do is extend the two forces that we are working with and label my pivot. And the shortest distances between these lines will be the arms of the force. So this is one of the arms, 15 centimeters, and this is the other arm. So of course, always the shortest distance is always a perpendicular line to these dot dash lines I drew. This is 3 centimeters. And of course, we can see that the force F would rotate the block this way, whereas gravity would rotate it this way. So these two have to be equal, and that's when it's about to tip. So what we can say is that the force times 0.15, so that's the torque of that force, has to be equal to the torque of the weight, so 0.3 times mg. So F is just 2 times mg, and our mass was again 1.2 kilograms, so this will approximately be 2.4 newtons for the force. So that's how we can solve this, and we have to outline why the box does not slide. So we have to think back to what our maximum force for the block was 4 newtons, and well, the frictional force here would be only equal to the force that we are pushing with, so that is not big enough. So F max, or I could say F frictional max from static friction is larger than 2.4 newtons, so it is not enough to kind of get the block moving. What we can kind of think about here is just taking this force and translating it down onto the ground, and that would kind of be the force that is pushing it along the ground. So we can move it here. We don't really talk about this in IB, but if we want to move a force from one place to another, we also have to consider the torque of that force. There's a way of reducing forces to other points on a system, but Again, that's not really part of the IB, but we can just imagine this force acting down over here, and that would be the one that's trying to slide it over the ground, but that's clearly not big enough to overcome the static friction. Okay, so these were the questions that I prepared. And as usual, if you want to see the rest of my solutions, then check the link out in the description.